Can chemistry determine the course of history? 1945, Japan. Two nuclear explosions devastate Hiroshima and Nagasaki, doing what 6 years of fighting could not do: end the Second World War. Who would have thought that its reason would be one of the smallest structures known to man, the atom? In today's show, we will trace the history of the discovery of subatomic particles. We will start with Dalton's atomic theory. We will then study the discovery of electrons, protons, and neutrons. We will also learn about atomic number, mass number, isotopes, and isobars. Finally, we will tackle important exam questions in Exam Decoded. If you are a lover of science history like me, then you are going to love today's show, because we will be stepping into the shoes of all those wonderful minds who led the way into the subatomic world and discovered what lay within. No history of the subatomic world can begin without the man who is considered the father of atomic theory, John Dalton. In the early 1800s, this Englishman published papers that suggested that the atom was the ultimate particle of matter, which could not be further broken into smaller particles. A revolutionary finding for its time, Dalton's atomic theory was able to explain the laws of conservation of mass and constant composition. However, his theory did have limitations. It could not explain the results of many experiments like the production of static electricity, which is actually the flow of electrons. Those answers would come a few decades later with the groundbreaking finding: atoms were not the smallest unit of matter after all. In 1830, Michael Faraday was working in the field of electricity and magnetism. That's when one of his experiments showed results that proved there was more to the atom than was earlier believed. In the exams, you could be asked what exactly his experiment was all about. So let's find out. As we mentioned, Faraday used a cathode ray discharge tube. This is basically a glass tube with electrodes that are made of metal plates. When high voltage is applied between the electrodes, current begins to flow from the cathode to the anode. This flow of current is checked by coating the area behind anode with a fluorescent material which glows. Faraday's experiment showed that cathode rays started from the cathode and moved towards the anode. These rays were not visible themselves, but their effects were observed thanks to fluorescent materials. In electric and magnetic fields, cathode rays behave like negatively charged particles, and thus it was suggested that cathode rays are made of negatively charged particles. These particles were called electrons. Characteristics of cathode rays do not depend on material of electrodes or the nature of the gas used. Faraday's observations suggested that electrons are an atom's basic constituent. But what was the nature of an electron? That's what scientists J.J. Thomson and R.A. Mulliken tried to understand. Pay close attention as I describe their experiments in detail, because it's a favorite exam question. Let's study Thomson's experiment first. Like Faraday, he too used a cathode ray tube to determine the charge to mass ratio of an electron. Thomson's cathode ray tube contained gases, and he applied electric and magnetic fields in such a manner that these fields were perpendicular to each other as well as to the path of the electrons. As the electrons interacted with the electric field, they got deflected and struck the fluorescent screen at A. In the magnetic field, the electrons hit at point C. On applying both electric and magnetic fields of equal strength, there was no effect at all, and the electrons hit at point B. From these experiments, along with other calculations, Thomson observed that the value of charge to mass ratio is 1.75 into 10 to the power 11 coulombs per kilogram. Now that the ratio of charge to mass was known, it was time to determine mass and charge accordingly. This was determined by R. A. Mulliken, who conducted the oil drop experiment. Here is what he did. He carefully balanced the gravitational and electric forces on tiny charged droplets of oil suspended between two metal electrodes. Knowing the electric field, the charge on the oil droplet could be determined. Since all electrons have the same charge and mass, he found the charge of electron to be minus 1.609 times 10 to the power minus 19 coulombs. Using this information, he was able to determine the mass of electron as 9.1 into 10 to the power minus 31 kilograms. The discovery of the electron was a huge step forward in understanding the atom. But there was still a crucial piece missing in the puzzle. If an atom is stable and neutral, it must contain more than just negatively charged electrons. Can you guess what that particle could be? That's simple, a positively charged particle. And so, finding this particle became a hot quest among scientists. Modified cathode ray tube experiments were conducted in which positively charged particles or canal rays traveled from the anode to the cathode. The charge to mass ratio of these particles was dependent on the nature of the gas in the tube, and some particles even carried multiples of fundamental charges. The pieces of the puzzle finally came together in 1934 when the neutron was discovered by James Chadwick. During his experiments, he observed a particle which had a mass slightly greater than protons. He called them neutrons. The picture of the atom seemed to be complete. Well, we have successfully discovered the constituents of an atom. So here is a question for you. Name the various particles in an atom along with their characteristics. While you go over your notes, I will take a short break. Stay tuned for the answer. Welcome back. Before the break, I had asked you to name and describe the different particles of an atom. Well, the atom is made of negatively charged electrons as well as positively charged protons that share the same magnitude. Besides this, the atom also has neutrons which have no charge and have a mass slightly greater than a proton. If you get this question in the exam, remember that you need to mention both charge and mass of the particles. In the previous segment, we saw how various scientists discovered what an atom was made up of. But how do these constituents arrange themselves in the atom? Again, it was J.J. Thomson who proposed one of the earliest subatomic models. And remember, this was much before neutrons were discovered by Chadwick. Thomson visualized the atom to be spherical in shape with a uniform distribution of positive charge, where electrons were inserted so as to balance the positive charge and make the atom neutral. While Thomson's model could support the neutrality of an atom, it fell short on explanations when it came to certain experiments, like those of Ernest Rutherford. His idea was to bombard atoms with alpha rays, figuring that this would effectively investigate its insides. In case you are wondering, alpha rays are positively charged subatomic particles. In his experiments, he used a gold foil which was bombarded with positively charged alpha particles. The gold foil was surrounded by fluorescent screens which gave a tiny flash as alpha particles struck it. According to Thomson's model of uniform distribution of protons and electrons in an atom, it was expected that the alpha particles would get deflected. But the actual results were surprisingly different. Most of the alpha particles passed through the gold foil undeflected, suggesting that most of the space in the atom was empty. A small fraction of alpha particles were deflected by a small angle. This would have been due to repulsion by nucleus concentrated in very small volume. All these observations helped Rutherford conclude that the model of an atom was not unlike the solar system. At its center was a positively charged nucleus containing protons. This nucleus was surrounded by electrons that moved in circular paths called orbits. Further, since electrons and the positively charged nucleus were oppositely charged, they were held together by forces called electrostatic forces of attraction. The radius of an atom was found to be about 10 raised to power minus 10 meter, and the radius of the nucleus was found to be about 10 raised to power minus 15 meter. The full picture of the atom seems to have been understood. Now it's time to define atomic number and mass number. Atomic number, denoted by Z, is the number of protons, which is equal to number of electrons in a neutral atom. Mass number, denoted by A, is the sum of protons and neutrons. Another point to remember is that protons and neutrons are collectively termed as nucleons. Now in exams, many questions give you the atomic and mass numbers of the elements according to their scientific notations. Let's learn what these notations are. Here is how atomic numbers and mass number are represented in scientific terms. X represents the element, A is the mass number, while Z is the atomic number. I am sure some of you have come across certain elements which have the same mass number but different atomic number. These are called isobars. Let's see some examples of isobars. Take a look at carbon-14 and nitrogen. They have the same mass number, that is 14, but their atomic numbers are 6 and 7 respectively. On the other hand, isotopes are atoms of same element with the same atomic number but different mass number. For example, chlorine 35 and chlorine 37. They share the same atomic number 17 but have very different mass number, that is 35 and 37 respectively. Time to take a question from one of our callers.
My question is, Why do isotopes of the same element show same chemical behavior?
Brilliant question. As I just told you, isotopes are atoms with the same atomic number but different mass number. Now, the chemical properties of an element are controlled by the number of electrons, which, as you know, is determined by the number of protons. Also, neutrons have no effect on chemical properties. So, all isotopes of a given element will show the same chemical behavior. It's time for another break now. But before I go, here is some trivia for you. Which instrument is used to observe the surface objects at an atomic level? It's an instrument called a scanning tunneling microscope and was invented by Gerd Binning and Heinrich Rohrer. Welcome back. We have been talking about the discovery of subatomic particles on today's show. Here is what we have learned so far. Dalton proposed that matter is made up of indivisible units called atoms. Protons are positively charged, electrons are negatively charged, and neutrons are neutral. Atomic number is the number of protons in nucleus of an atom, which is equal to number of electrons in neutral atom. Mass number is the number of protons and neutrons. Isobars are the atoms with same mass number but different atomic number. Isotopes are the atoms with same atomic number but different mass number. With that, it's time to take on exam questions with Exam Decoded. Welcome to Exam Decoded. Leave your exam worries behind because we have got tips and insights that are guaranteed to boost your scores. Now, we all know that exams are serious business, but I think they can also be a fun challenge, like our rapid fire round. Here is how it works. I have 5 questions for you. You need to answer them in under 5 seconds. Every correct answer fetches you 1 point. Easy enough. Let's get started. Here is an easy start to the round. Dalton's atomic theory regarded the atom as the ultimate particle of matter. True or false? The answer is true. Your next question. In a cathode ray discharge tube, the positive electrode is called cathode. True or false? I hope you answered false because the positive electrode is called the anode. Cathode is the negative electrode. Your third question for 1 mark is, protons are also called canal rays. True or false? If you remember the cathode ray tube experiments, you will know the answer is true. Your fourth question. Fill in the blanks. Mass number denote the number of A. Number of protons, B. Number of neutrons, C. Number of protons and electrons, D. Number of protons and neutrons. The correct answer is D. Mass number is the number of protons and neutrons. We are in the home stretch now. Your last question. Rutherford's alpha particle experiment with gold foil demonstrated the existence of which part of the atom? A. Nucleus, B. Energy level of the atoms, C. Neutrons, D. Electrons. Remember all those alpha particles that got deflected? Then you will know that the correct answer is A. The nucleus. Now let's add up our marks and let's see how well we have done. If you have got a perfect score, you are our high flyer. Keep it up. If you have got 4 or 3 points, then you are an achiever. Good work. Just a bit more practice and you will be ready. If you have scored less than 3, then you are a learner. This means you still need to brush up on this topic. But don't worry, we have just the remedy for you. Log on to www.topperlearning.com and try our practice tests. Okay, let's take a closer look at exam paper trends now. Well, the discovery of subatomic particles accounts for 6 marks out of 70, which makes it important. You are likely to be asked very short answer type questions for 1 mark and short answer questions for 2 marks from this topic. And these questions most often test your knowledge ability. I am sure you have all been told that knowledge is power, but only if you use it well. And your exams mark you not just on what you know, but on your stepwise presentation. Let's see an example of one such question. Explain Rutherford's conclusions on the structure of atom. This is a 2-mark question of average difficulty. This answer can be divided into 4 sections, each for a half mark. The first part is Rutherford's conclusion regarding structure of atom is based on his alpha particle scattering experiment, in which a gold foil was bombarded with positively charged alpha particles. The gold foil is surrounded by fluorescent screens which give a tiny flash as alpha particles strike it. This much for half mark. The second is most alpha particles pass through the gold foil undeflected, which suggests that most of the space in atom is empty. Another half mark. The third part for half a mark is small fraction of alpha particles was deflected by small angles. This was due to repulsion by protons, which must have been concentrated in a very small volume. The final part of the answer is the volume occupied by nucleus is negligibly small as compared to total volume of the atom. Final half mark. Now let's go over to an expert for some handy tips.
The topic discussed in today's session are theoretical, and hence you must go through the visual illustration shown to you very thoroughly. In the Rutherford experiment, he observed 3 points and he made 3 conclusions based on that. Students, you are advised to remember these 3 observations and 3 points very specifically. Mass number is greater than atomic number always. Students, you are advised to practice more regarding the calculation based on atomic number, mass number, number of neutrons, protons and electrons, because very frequently questions based on these may be asked in the examination.
So when it comes to your exams, don't have an electron cloud hanging over your head and always have a positive attitude. See you next time.